Good morning, everyone. This is Samvita, currently studying second semester in civil engineering of IIRA College. So today I'm going to explain about water treatment systems from crisis to clean water solutions, a comprehensive exploration of technologies, innovations, and policies transforming the global water crisis into sustainable solutions for all communities. So my goal is to explain what, why, and how of the modern water systems. So coming to introduction, it starts with the auxiliary of life concept. So every living being, humans, plants, and animals depends on water. The problem is that we mentioned the traditional systems are failing due to rapid population growth and climate change. In India, for example, we have 18% of the world's population, but only 4% of its water resources. So the solution is that traditional wisdom. We have to revive ancient methods like rainwater harvesting and check dams that recharge groundwater. Smart technology. We have to introduce smart water management using LOT sensors and real-time monitoring to detect leaks instantly. And sustainable practices. Highlight drip irrigation in agriculture, which delivers water directly to roots, reducing waste by up to 60%. And the conclusion is to call for a shift from reactive to proactive management. Everyone from governments to individuals must be water hero. And the key content blocks for a detail thing is that current global status is one-third of those in water-stressed countries are under critical threat. Water scarcity could cost some nations up to 6% of their GDP by 2050. And components of management systems are source management, which are protecting rivers and aquifers from pollution. And distribution, upgrading infrastructure to stop the 40% loss typically, which is seen in leaks. And treatment and reuse, implementing wastewater recycling for industries and gardening. The water, energy, food. So explain how water is needed for energy, cooling, power plants, and food. 70% of global water goes to agriculture, making its management central to all economic stability. And the tips for impact is that compare groundwater to a bank account. If you withdraw more than you deposit through rain, you eventually go bankrupt. So when you relate to reality, you have to mention local issues like drying bore wells or erratic monsoon patterns to make the threat feel personal. And you have to save water properly and use water properly and efficiently. The global water crisis in number one. So 785 million. There are 785 million people without safe water, still lacking access to safe drinking water globally. So according to the United Nations 2025 report, 785 million people worldwide still lack access to safe drinking water. So that's equal to entire population of the United States plus Canada combined. So this strategic number represents families forced to drink contaminated water daily. So children missing school due to waterborne illness and communities trapped in cycles of poverty and disease. So this crisis spans continents from rural villages in sub-Saharan Africa, where women walk miles to collect water from polluted streams, to urban neighborhoods in developed nations, where aging infrastructure delivers lead-laced water to homes. Climate change intensifies the challenge, causing droughts in some regions while flooding contaminates supplies in others. So what we must remove? Contaminant cheat sheet. So understanding water contaminants is essential for designing effective treatment systems. Each category requires specific removal strategies and concentrations vary dramatically. So from bulk ions measured in milligrams per liter down to trace toxins in micrograms per liter. So coming to Mesa inorganic, so calcium, Ca2 plus, sodium, Na plus, and nitrate, NO2 minus. And the concentration is 1 to 1000 mg per liter. So these common ions affect water hardness and taste, but generally pose low health risks at typical levels. And coming to next one is minor inorganic toxins. So arsenic, lead, and mercury. Concentrations of 0.1 to 10 mu grams and milligrams per liter. As WHO limit for arsenic is 10 milligrams per liter. So these heavy metals cause cancer, neurological damage, and organ failure even at trace levels. And the next one is anthropogenic organics like benzene, PCE, TCE, and pesticides. The concentration is 1 milligram per liter to tens of milligram per liter. So industrial solvents and agricultural chemicals that bioaccumulate and cause long-term health effects. And pathogens. E. coli, Giardia, viruses, protozoa. The concentrations are millions per liter. So microorganisms in untreated sources causing immediate illness require disinfection to eliminate. And the classic 9-step municipal tree. So traditional municipal water treatment follows a proven sequence that progressively removes contaminants. This multi-stage approach, detailed in Mihalik and Zimmerin 2024, ensures consistent water quality while providing redundancy. So each step backs up the others. Here's how water travels from raw source to safe drinking water. Screening removes large debris, leaves, and sticks using mesh screens. And next one is aeration. Adds oxygen to oxidize iron and manganese, removes volatile compounds. And the third one is pH correction. Adjusts acidity to optimize coagulation and prevent pipe corrosion. The next one is coagulation and flocculation. Chemicals dump fine particles into larger aggregates for removal. And the next one is sedimentation. Gravity settles flocks to bottom, clarifying water before filtration. And pre-chlorination. Initial disinfection to kill surface pathogens and reduce organic load. And filtration. Passes water through sand, activated carbon, or membranes to remove remaining particles. And disinfection. Final pathogen kill using chlorine, ozone, or UV light, which creates a residual protection. And the final pH judgment is that ensures water is non-corrosive before entering distribution pipes. And coming to disinfection, which is showdown, which killer wins. So choosing the right disinfection method balances effectiveness, cost, safety, and residual protection. Each technology has strengths and limitations. So modern plants often combine methods for maximum reliability. Coming to chlorine, its effectiveness is 45 minutes contact and 1.1 milligram per liter residual. And downside is it creates trialahormines THM's EPA 2024 limit is 80 milligrams per liter. And it is best for municipal systems, which is needing residual protection and distribution pipes. And coming to ozone, its effectiveness is 99.9% virus kill, no residual formed, and the cost is $0.30 per m square and 2025 phone expired. And it is best for bottling plants and facilities with short distribution. And coming to UV light, efficiency is 0.02% energy of traditional UV, and the limitation is it is effective only on clear water. Turbidity blocks UV, and it is best for clear groundwater sources and point of view systems. And coming to advanced oxidation, the method is H2O2 plus UV light, which creates hydroxyl radicals, and status is emerging fourth generation. Disinfection approved by EPA in 2025, and it is best for destroying persistent organic pollutants and pharmaceuticals. And emerging technologies as reshaping treatment. So 2024 to 2026 innovations are that water treatment industry is experiencing its most transformative decade in decades. So from nanomaterials to artificial intelligence, these breakthroughs promise cleaner water at lower cost, and they are already being deployed in pilots across the United States and globally. And graphene oxide membranes, AI-driven sensor networks, electrocoagulation units, and modular microtreatment pods. And the case study is Greeley, Colorado, a sustainable retrofit. So in 2025, the city of Greeley completed a comprehensive upgrade to its municipal water treatment plant, transforming an aging facility into a model of sustainability and efficiency. So the project demonstrates how existing infrastructure can be retrofitted with cutting-edge technology with requiring complete replacement. So designing team as Arcadis-led engineering, David Von Reden managed construction, and Ben Patrick Tidrear handled regulatory compliance. And key upgrades are that they installed UV LED disinfection, replacing chlorine contact tanks, added a preamble membrane filtration for microplastic removal, and integrated solar-powered pumps to reduce grid dependence. And the results are 96% reduction in total call-in forms compared to 2019 baseline, and 30% low energy use despite 15% of population growth and elimination of THM formation. And the clean water at a corner of Main and Second. So modular microtreatment pods bring municipal quality water to communities that could never justify a full-scale ban. So these self-contained systems serve populations of 200 to 500 residents, providing safe drinking water without the need for miles of pipeline or millions in infrastructure investment. And financial and policy, money meets science. So transforming water infrastructure requires more than technology. It demands political will, public funding, and regularly framework that incentivize innovation. So recent federal and state actions are accelerating the adoption for advanced treatment systems. And Infrastructure Investment and Job Act according to 2024, is that $1.2 billion earmarked specifically for advanced treatment upgrades at municipal plants nationwide. And EPA-led action level 2025 that tightened to 5 ppb from previous 15 ppb limit. And state-level incentives. California's SB 1005 provides grants for AI-enabled monitoring systems. So call to action. So, according to 2030 vision is that the technology exists today to ensure every American has access to safe, affordable drinking water. So, what's needed now is a collective action from policymakers allocating funding to engineers adopting emerging technologies to communities demanding accountability. So, here's our shared version of 2030. So 100% compliance. Every US municipality meeting Safe Drinking Water Act standards with real-time monitoring and public transparency. So graphene revolution. So deploy graphene oxide membranes at 30% of large-scale plants, cutting desalination energy cost by 70%, and AI optimization. So leverage AI sensor fleets to cut chemical yield by 40% and achieve net zero emissions at treatment facilities. And my rule is that champion funding initiatives. So adopt emerging technologies and advocate for policies that turn today's crisis into tomorrow's clean water reality. The time for action is now. Every day without clean water costs lives, limits opportunity, and perpetuates inequality. Together, we can build a future where safe water flows to every tap. Thank you.